Good afternoon, everyone. My name is Kim Tran. I'm currently a faculty member at Clarkson University. Today, I will discuss about our main research findings in last few years on seismic waveform tomography. The topic of this talk is the sinkhole detection and characterization with 2D and 3D full waveform tomography. So the goal of this research is to identify the embedded void with only surface measurement of the seismic wave on the ground surface. So here we put the sensor or geophone on the ground surface. We generate a seismic wave, propagate through the medium, carry the information of the soil and rock, and then measure on the surface. And then we do the waveform analysis to extract the material property of subsurface structure. So here we have a shear wave velocity profile. We have a blue zone on the top here, soil. The red area here is limestone. The blue zone inside the limestone here is a void. So the goal is to measure the data on the surface and then identify the embedded void, go to 50, 60 feet depth like we usually do with our equipment.
Are we allowed to ask a question or two?
Yes, sir. Yes, sir.
Okay.
Yeah, please interrupt if you have a question.
Okay.
All right.
Because I'm going to be asking you if you have water in there in a bit.
Yeah,
so
yeah.
You have
right.
shear and compression.
Shear and P wave. Yeah.
But
So air field void, we have a P wave about 300 meters per second. Water field void, we have a 1500 meters per second. So this is the outline of the presentation. I will talk about the need of the sinkhole detection a little bit, the full waveform inversion, motivation, and challenges at geotechnical scales. A quick overview of the full waveform inversion methods. I will talk about 2D and 3D full waveform inversion methods. So for 2D, we'll talk about the methodology, synthetic data application and real data application for sinkhole in Florida and abandoned mine void in Ohio. And for 3D full waveform inversion, we developed two different methods using Adjoint gradients and Gauss-Newton methods. And we'll have a synthetic data application using the both methods and compare the results. And I also talk about the first field data application using the two developed methods and compare the result with the invasive test, in this case, SPT. And then I will finish the presentation with the conclusion. It's not working. Go too quick.
There's a gremlin in the computer.
Yeah.
You want to operate?
Can you hit? Yeah.
It might work better from the keyboard.
Yeah, yeah.
I think it's done, but...
So that is the need of the sinkhole detection. Sinkhole cause significant problem during and after construction of the foundations. So they can cause the structural collapses that lead to significant property damage or even fatalities. So shown here are two examples of sinkhole collapses in Florida. The top one swallowed the whole house. The bottom one destroyed a resort complex near the Disney World. So these collapses are a result of poor site characterization. So if we use only traditional invasive tests, SPT, CPT, we actually test less than 0.1% of the material supporting the foundation. And the chance of identifying the embedded void is very small. And we can accidentally build the building bridges on top of the voids, and we may see this collapses. And seismic method can help us to test over large volume of material because they typically faster and cheaper than invasive tests. And we can obtain the soil rock property stratigraphy or can identify the embedded void anomalies with only surface measurement. I will talk about the motivation of the full waveform inversion. So most of the conventional seismic method analyze travel time of certain wave types. So for the refraction tomography uses inversion of the P wave first arrival signal to determine the P wave velocity profiles. Surface wave method use inversion of surface wave dispersion property to determine shear wave velocity profile. Migration method, migrate the waveform with depth, determine the layer boundaries or the boundary of the anomalies. Wave equation, full waveform inversion approach is wave equation based and has potential to use full information content or waveform of the measured data. So it uses both phase and magnitude of the measured data, because conventional method only use the phase velocity without the magnitude of the measured data. And full waveform inversion has potential to consider all measured wave type, P wave, shear wave, Rayleigh wave. And it has potential to characterize both P wave and shear wave velocity profile at high resolution. So it can go meter pixel down to 20, 30 meter down. So shown here an example of real measured data in the field. So horizontal axis here is the receiver position. That is 2D problem. Vertical axis is time domain. So the signal propagates through the void or soft material takes more time to travel and will show up as the later point in the measured data. So if we use only first arrival signal like refraction tomography, we miss the entire information of the void. We need the later point in the measured data to identify the void. So here we match entire measured data to extract the P wave and shear wave velocity profile. So although the full waveform inversion is attractive, has potential for high resolution material imaging, but there are a number of challenges at geotechnical scales. And I would like to draw your attention on these challenges, and I will address it in our method. If we don't address these challenges well, we get not so much of the result out of the full waveform inversion. It's just stuck at first few meters of the shallow depth. We cannot resolve deeper structure. So for seismic testing, if we use a sledgehammer to generate the wave field, the wave citation is not consistent, basically. We don't apply the same load at each source location. We don't measure the source signature. So inconsistent wave citation, unknown source signature, produce inversion artifact near the source location, first few meters around the source location. We often see the variable soil rock at first few meters, and coupling with the poor priori information in initial model will generate the shallow inversion artifact or local minimum. So we see a lot of anomalies first 5 meters, but we don't see anything deeper than that. And the biggest challenge is the dominant wave, Rayleigh wave, at small scale. So 2/3 of energy is converted to the Rayleigh wave. And body wave propagate up and down, refracted is small. And we want to increase the contribution of the body wave. So we have to suppress the contribution of Rayleigh wave and increase the contribution of the body wave so that we can solve the problem deeper. We can characterize a deeper substructure. So dominant Rayleigh wave, small body wave will generate large model update, shallow artifacts at first few meters, and poorly resolved deeper structures. Yes, sir.
Does that mean that you should also be using sources at depth?
If we can embed, it is better. So if you have the invasive source or embedded sensor, always better. So we are talking about borehole tomography now, because this one limited at first 30 meters.
How deep do you want to go?
It's depends.
So isn't the first 30 meters?
It's important, right?
Right.
Yeah.
I mean, isn't that a very good, I mean, if you can identify anomalies there that might be sinkholes, isn't that where the bulk of them will be that affect the public?
Yeah, would be the main interest.
Okay, just a question. Because with the ability to push sensors and push things into the ground, means you can push a source down into the ground that you could then also load at depth that would be only body waves.
Yeah, that's perfect.
Okay.
That can improve the resolution if we have a more body weight.
we can do that.
Yeah, that's what we want. Like we do,
Okay.
yeah, we do embedded source.
Well, we're just, well, that's, we'll see about what water does to us, but no, now you could be doing mainly shear waves that you're generating at depth too. I mean, it'd be shear and P, but the P is gonna
So of the water,
be mainly
right?
influenced by the water.
Yeah,
We're not
1500
really
meter per
in
second.
real stiff rock or anything.
Now, yeah.
I'm sorry. Just a thought.
So in our method, we will address most of these challenges. Next. So I will have a quick review for the full waveform inversion. So the goal is to determine the shear wave and P wave velocity profile of the subsurface structures. We conduct seismic testing, generate seismic wave, and measure the wave field on the ground surface. And then we do inversion to extract the VS and VP. Hereafter, I call that model AMP. So for site characterization, we divide the subsurface structure into several thousand cells and determine the VS, VP of individual cells. So we can build the S wave image, P wave image like this. And then we can identify the void, for instance, in this case, inside the limestone, based on the shear wave image. So we are solving the problem of a few thousand unknown for 2D, 20, 30,000 unknown for 3D, or even larger than that. So to solve the inverse problem, we need the forward modeling and model updating. So the forward modeling is to describe relationship between the measured data or seismic wave as a function of material property M. So here D is a function of M. So here is physics-based modeling. So we use two-dimensional, three-dimensional wave equation to model the wave field to generate the so-called estimated data. So we have an estimated seismic wave, D estimate, as a function of estimated material property or shear wave and P wave of cells. And then we will do the model updating. That means we will find the best model AMP.
You're not including your source wavelet in this formulation in your model?
Yeah, I will address about that later.
Okay.
So here we will solve partial differential equation to have estimated data as a function of estimated material property. And then we will match estimated data with the measured data from the field to extract the material property VS and VP here. So we will use global optimization or deterministic optimization to find the solution. So this is iterative process. So matching the signal. So during my PhD, I did symmetric annealing and genetic algorithm with the supervision of Dr. Hiltonen. And then after that, we did the deterministic approach, Newton, Gauss-Newton, gradient approach. So now I will talk about 2D methods. So the 2D method will include the forward modeling and model updating. So forward modeling, we use two-dimensional wave equation. So we have equation governing particle velocity, equation governing stress tensor, and we use finite different method to solve these equations. So in the field, we measure the data in an infinite medium of the Earth. But when we model, we can only model a finite medium. So we have to treat the boundary with the special boundary condition so we can avoid artificial signal reflected from the boundary. So here we use a so-called that perfectly matched layer boundary condition at the bottom and two vertical boundary. So here you can see we do the comparison with and without the perfect matched layer. So the top one, the signal propagates through the boundary without reflected. The bottom one, the signal reflects back from the boundary. We don't want that. That is artificial signal. We want the signal reflected from the void, not from the artificial boundary. Next, please. So for the model updating, we use Gauss-Newton method to match the measured data with the synthetic data. So this method was developed for the sledgehammer waveform. So we have to deal with the inconsistent source signature. So here we develop a method so-called that source independent inversion. So we can use any source signature for the inversion. So here's the trick. We F here the simulated data from the wave equation. We convolve with one channel. We call that reference channel from the measured data. It's similar to the source. So you get synthetic data convolved with one channel from measured data. And then you get the measured data for all the channels convolved with one channel from synthetic data. So we kind of compare apple to apple here without knowing the source signature. So by doing that, so we get entire measure synthetic wave field convolved with one channel of the measured data and get entire wave field of the measured data convolved with one channel from the simulated data. So the inversion become independent of the source signature. So we can use any source signature for wave simulation to answer the question, right? So we can use Richter wavelet, we can use psi function or even a triangle wavelet to simulate the waveform. And then we do convolution like this. So we don't need to know the actual force applied into the ground because we don't measure it using the sledgehammer. So for example, we can use Richter wavelets like this. We can use unit, magnitude, and then any delay time. All requirement is the frequency content of the source signature is similar to frequency content of the analyzed data. So for instance, we do 10 Hertz analysis. We need to put the central frequency of the source signature 10 Hertz. And then for the model updating, now we match the synthetic data with the measured data to extract the material property, which is a model M here. So model M here is a vector of a few thousand unknowns, Vs and Vp of cells. So we want to determine the model M here. No, can you go back to previous one, please? So model M at iteration n+1 is updated from previous iteration by this equation. So J times delta D here is the gradient. We can determine that from Gauss Adjoint method. So most of the full waveform inversion method out there only use this term. They don't have this lengthy inverse matrix. This is the inverse Hessian matrix. And it's very important for the void detection. And it's filter the gradient vector and focus on the void. And balancing the gradient vector, that means we can update the entire model with similar magnitude. So we can solve deeper structure and shallow structure at the same time. We don't have to go from shallow to the deep structure. I will have a comparison with and without this term. So because we do the convolution and then J here is Jacobian matrix. So which is derivative of wave field with respect to individual cell. So here we use virtual source and reciprocal waveform to calculate the Jacobian matrix for all the cells harmoniously. So implicit method. So alpha here is just step length in this equation, and lambda 1, lambda 2 here is just for regularization to control the roughness of the model. So smoother model, less artifact, and rough model will generate more artifacts. So we can control the smoothness of the inverted model by lambda 1 and lambda 2. Next, okay. So I will have a comparison of Gauss-Newton with the cross-adjoint gradient method. So for example, we have very simple model like this, homogeneous soil with a void inside. Very simple model. So here we generate the data on the top and then do inversion for initial model homogeneous soil. So to see if we can identify the void quickly. So here is a gradient for cross adjoint. You can see we identify the void in the P wave shear wave gradient, but there are a lot of artifacts here. You can see this is due to the free surface condition. And when we do the Gauss-Newton inversion, we can see we can filter and focus on the void location in both shear wave and P wave image. So we remove all the shallow artifact here, all the shallow artifacts. Focus on the void location only. So this term inverse Hessian matrix is particularly important for void imaging.
So Kim, so we have 3 columns. The very right column is the one, the reconstructed material.
Yeah, so this is inverted result for first iteration. So you get initial model, subtract this one, you get this one. So this is shear wave and P wave profile. We don't see anything from the cross adjoint method.
So what does this second column mean? What does this second column or this full figure?
This column?
Yeah.
This is the gradient vector.
Gradient vector.
So you get the initial model, subtract the gradient vector time with certain time step length, and then you get the inverted result. So cross adjoint or traditional full waveform out there do this one. So you see the void here in the shear wave, but not so much in the P wave, and a lot of shallow artifact. So if we bring it to the field, it's just stuck at first 5 meters. We don't see it deeper. For the Gauss-Newton, you see it very clearly void after just one iteration. So if we have a homogeneous soil and a void there, we don't need to run inversion very long. Just one iteration, you see the void location right away. But if we have a layer and then we have to solve the layer first, so we need longer run. So if we have variable rock, we have to solve for interface first, and then we'll show the void later. So
does this mean that most of your resolution is always coming from the body waves?
Both Rayleigh wave, but we suppress the Rayleigh wave. Okay. That's what I mean, because shallow artifacts mostly due to the Rayleigh wave. So we kind of increase the contribution of the P wave with depth.
Does that mean that you would like to use high frequencies because that would suppress the Rayleigh wave at deeper depths? Am I saying that correctly? In other words, high frequency short wave Rayleigh waves would then be suppressed at deeper measurement points, and just body waves would be sampling that material?
Yeah, it's difficult to measure high frequency component on the ground surface because it's still dominant by Rayleigh wave. So it's still stuck by the Rayleigh wave. You cannot separate in time domain.
True.
Right?
True. Yeah.
So it mixed together in the geotechnical scales. So that's why our scale is kind of more difficult than large scale. We don't have a problem with the computer, but we have problem with the Rayleigh wave. So we cannot separate them. For the data acquisitions, we need to put the geophone and active source on the ground surface on top of the void. So that is the main limitation of the 2D method. So we need to run line here, and so on to cover the whole area. So line by line. Later, we'll talk about 3D, and then we can put the 2D grid of the sensor on the top. And we put the geophone and source from 1 to 3 meters spacing. We used 10 to 20 pounds sledgehammer or a propel energy generator to generate the wave field. So from 5 to 50 hertz. And then when we apply the vertical load, we generate all type of wave, Rayleigh wave, P wave, shear wave, and we measure all of them on the ground surface. And we have to use all of them because we cannot separate them. So you will match entire measure data to extract the P wave velocity and shear wave velocity. So for the data analysis, we address the issue of the highly variable rock poor initial model by starting the analysis with lowest frequency. So usually we go from 5-10 hertz range, and then we increase the frequency for the next inversion runs. So Low frequency, we have large wavelength, require less detail of initial model or initial guess. And then a misfit function look like this for low frequency. We just have a one global minima, so it's easy to find. But if we have a higher frequency and then we have a multiple local minimas, so sometimes if we don't start with a good initial model, it's stuck in the local minimum. So, and then by adding the high frequency data gradually helps to resolve the near surface structure. So we begin with low frequency, so deeper depth, and then add higher frequency to get more resolution at shallow depth. And before applying to the field, we did synthetic tests to see how it works. Right? If it does not work on the synthetic data, it will not work on the field. So there is no point to collect the data from the field. So that is.
May I ask, in terms of a source at the surface, if you could deal with a frequency at a time, I'm not saying that makes the field fast, but you would be solving then each one of those separately.
That's frequency domain.
Yeah.
Yeah, we do both. We do both.
Okay.
Later on, we'll talk about frequency domain inversion in 3D. So here we do time domain. Because time domain, we have a consistent magnitude. Initially, we did frequency domain, and then the magnitude from the waveform generated from sledgehammer is not consistent.
Oh, that's right.
Yeah. So we have the peak up and down everywhere. So we cannot select a consistent component to do inversion. So that time domain helps.
When we're doing surface waves with hammers, we have different hammers because they generate different frequencies.
Yeah.
And we want small hammers for high frequencies right near the surface.
Yeah.
Okay.
So here we talk about the time domain inversion. So for instance, we have a hypothetical soil model, 3 layers. So we have a soil on top, rock at the bottom. The blue box here is a void having shear weight to 0, P weight to 300 meters per second. Airfield void. Generate the data using 24 receiver, 25 short location on the ground surface or depth 0. Data look like this for the first shot at depth distance 0, shot 13 in the middle. So we have 25 of them. We assume this is measure data from the field, do inversion to see if we can recover this true model, to see if we can identify the void at 10 meter depth. So here is a true model, and this is initial model. So simple initial model increase the velocity with depth. I will talk more when we deal with the real data. This is inverted result at 5 Hertz. So we use the data from 2 to 10 Hertz here, central 5 Hertz. We start seeing the variable rock at the bottom, but not the void yet. So we solve for the layer first. And then we use this one like initial model for the next inversion run at 10 Hertz. We start seeing the void, and then 15 Hertz, and then 20 Hertz. That means we go up to 25 Hertz in this case.
Where does the initial model come from?
This one we can estimate it from the dispersion curve.
So is that from very low frequency? So could you put 1 Hertz where you have initial model and that's what you'd get?
No, it's surface wave dispersion curve on surface wave. Just taking 2D FFT of your waveform along the multi-channel array and looking at the dispersion curve.
So we have I will explain more for the real data.
Okay.
Right. So right now we just accept it. So we have a 200 meter on the top, 600 meter at the bottom for now. We can search for, this is just one unknown problem. Right? We know the velocity on the top, which is associated with high frequency.
Right.
Right. Bottom, we don't know. So we can search for multilinear slope. So we can search for different slope to find the best model if we want to. And then we bring it to the field. So we did it several sites. So far, the method worked well for more than 20 test sites in many states. And 2 of them with a void I will show here, one for Sinkhole in Florida and one for abandoned mine void in Ohio. So this is the Newberry site. We will use that for demonstration tomorrow. And Dr. Hiltonen will provide more detail about the site. But it is a dry retention pond, and with the water, it looks like this. So The site consists of 5 sand and sill underlain by variable limestone. So top of limestone from 2 to 10 meters at different locations. We divided it into 25 lines from A to Y, 3 meters apart. And when we did the seismic test, we did at the northern portion of the site, and there was no indication of the void. So this is a blank test. We try to see if we can identify a unknown void. So we don't know the void location, so we have to do multiple lines. So we did 10 test lines. Look like this. We did along line K to line T, so 3 meters apart. So 10 feet apart. We run line by line. 36 meters long for each line. We use 24 geophone and 25 sledgehammer shot. So we use 20-pound sledgehammer to induce seismic wave.
Now, when you say 25 shots, that's at one point or 25 shots?
Along the line.
25 shot points.
Yeah, short points along the line. So it's very dense test configuration here. Next. So here the initial model. So we began the analysis with the spectral analysis of measured data. So we have Rayleigh wave or shear wave around 200 meters at the high frequency, 30 hertz. And then it goes down to about 400 at the bottom. We don't know, it's kind of funky here. But we can search here as we begin with the 200 on the top, and then we search for the bottom. So we start from 200 to 1,000 at the bottom, and we try every 100 meters. So we do 300, 400, 500, 600, 700, and so on to 1,000 at the bottom. And we found that 200 on the top, 400 at the bottom fit the data best. So we use for initial model. So this is, we search for the best 1D model first. And then we found 2 lines with anomaly. Line P down to 15 meter, 50 feet depth, soil on the top, blue zone, variable limestones, waveform match very well, observe, estimated data, residual, low velocity zone here around 300 meters per second, so it's not void. It's just soft material. It's next to a void. So here it's like Q. We have very nice void here. Shear wave go almost to 0, about 20 meters per second in this case. So we have a very nice void here. Shear wave, P wave, very similar. Around here about 300 meters per second. So we think that is airfield void. And then we gave it to DOT. They did the verification a few weeks after that. So there exists a void at this location. So SPT go to 0. Next.
So that vertical line there was the SPT test?
Yeah. At the void location, we recommend it. So the next thing I want to talk about is abandoned mine void in Ohio. So they have about 8,000 abandoned mines in the states. About 1,200 land mines under land by mine voids. So they need to find the void and then stabilize it. So they try different entity methods, refraction tomography, GPR. They have a shallow clay layer, so they cannot go very deep with the GPR. Resistivity lose the resolution very quickly with depth. And then because the mine void is only 5 feet height, but lateral dimension is large. It kind of thin, but laterally very large void. So we did the next one. So we did seismic survey on the pavement. So that the site location located at the edge of a large abandoned mine complex. So around here, they don't have a mine map. So we don't know. That's why no subsidence on the surface. But you just want to know if there is a mine void near the mine complex. So overburden is interbedded clay shale, sandstone, variable bedrock at the bottom. So here we did on the shoulder of the pavement of the road. So here we use land streamer geophone. So simply we just put the geophone on top of the metal tripod. So we don't have to couple the geophone into the pavement material. So we tie all 24 geophones together so that we can move quickly along the road.
Are those 4.5 hertz phones?
Yeah, 4.5 hertz phone. And we use propel energy generator source. So now we can apply more consistent source.
The rubber band?
Yeah. We don't use rubber band, but it's a 40 kilogram hammer. So using a motor here, press the button, this one go up and down. So we can select the different height of the rope. So we can apply different energy if we want. And we can also change the impact plate a little bit to play with the frequency content.
So what is the predominant frequency range?
We only use from 5 to 50 hertz. So here's the result. So we did 2 test lines along the pavement. We found one segment with a few voids here. So the top one is shear wave velocity profile, down to 70 feet in depth. And then bottom one is P wave. So we recommended 3 locations, one here, and one here, because this one we don't see it in the P wave. So we did not recommend for them to drill it. So
you don't see it from P wave velocity. Water, is that?
Yeah, we think that is a very deep water. So it's okay. Not there. So it's still high.
Yeah.
So we don't think, if it's like this, it may be airfield void, right? And this one need to go to 300.
Right. So
and
if
it's
got a Poisson's ratio that would be nothing like 0.49.
No. Yeah. So they did the drilling, and interestingly, they found void at all 3 locations. We recommended.
Well, 2 out of 3 ain't bad.
3 out of 3.
Oh, I know, but I mean, but yeah, the 4th one they didn't drill in.
They did not drill it.
Right.
But usually, no, many times we will miss it. Many times we will miss it. But in this case, we did it very well. So they drill it, and they found the void, and they also do the sonar scanning to identify the boundary of the void. So sonar scanning is similar like this. And then they measure the travel time from the borehole to the edge of the void, and then divide it by the velocity to calculate the distance, right? So you know the travel time, you know the velocity in...
Is it water that they're using?
No water here, very deep. Okay. So they use 300 meters per second for the for travel in the air, pressure wave. So they can determine the boundary at different depth. So that is another company did it. So
why couldn't they do that video? I mean, optical.
I don't know.
I mean, with a light.
Yeah, so it's faster, right?
Camera.
Yeah.
Right, because if it's air filled, I'm just wondering.
Yeah. So you can lower camera and image it. So this is a boundary at different depth. So here is the void from 43 to 49 feet in depth, different boundary at different depth. So it's quite large with depth. So some location is like 40 feet length, 40 feet lateral, but it's very shallow, very thin in the vertical dimension. So very thin void. And we found that we can go up to probably 3 diameter of the void with the depth. So if you have a 10-foot void, we can identify down to 30 feet depth. Deeper than that, we don't see it very clear, but we see like a soft material joint. So still can identify probably down to 5 diameter depth. In this case, lateral dimension is large. So we can...
Total sense, doesn't it? I mean, in terms of the size of the void.
Yeah.
And you have to be.
Yeah.
Just like us in SASW, the thickness of the layer relative to the depth you're at.
Yeah.
So see that softer material.
So here the dimension is large laterally. That's why we can go down to 50, 60 feet in depth. Mm-hmm. And then the next thing I will talk about is the 3D full waveform inversion. So 2D work very well.
Can I just go back? So that one though, you're basically was a 2D survey.
Yeah.
Super impressive.
2D.
Yeah.
And we don't know lateral dimension.
Really 3D features.
Yeah.
You picked them up with a 2D survey.
So that's why we have to run it on top of the void. That is the main limitation. Or we can do another line next to it, right? So let's
How close?
1 diameter away from the void. That's we did 3D analysis. If we can put a sensor 1 diameter away from the void, we still see it, like 3D effect, because we do it plane wave, so it's still average laterally a little bit. So within 1 diameter from the center of the void, we still see it, interestingly. So here, 2D method work very well if we put the sensor on top of the void or near the top of the void. But now it's 3D void, right? So it's not very efficient. So we want to put a 2D grid of the sensor on the ground surface and want to see everything underneath the tested area. So we developed 2 different methods, Gauss-Adjoint and Gauss-Newton, because Gauss-Adjoint is quite straightforward. Most of the full waveform inversion method is based on Gauss-Adjoint method. So here we also use 3-dimensional elastic wave equation. So that is in compact form. The top equation governing particle velocity in 3 directions, x, y, and z. And the last 2 equations are 6 different stresses in 3D. So that is about 9 equations here. We also solve it using finite difference method and use perfect match layer at the bottom and 4 vertical planes. So shown here is an example of wave propagates from a point load on the ground surface in 3D. Go back, please. We don't see a lot of reflected signal from the boundary because we use absorbing boundary condition. So this is very similar to the wave propagate in the field. No boundary, just propagate away. So we only measure the data in the tested area on the top here. Right?
Did you use FDM in 2D reserve as well?
Yeah.
So or FDM.
Yeah. Finite difference, because we don't have to solve the inverse matrix of the stiffness matrix like finite element method. So it's faster, basically.
Is it faster?
Way past what light.
Yeah, that's some newer technology.
But FDM cannot model this, curve of the domain.
Yeah, we are working on that.
Yeah.
We use triangular element for the finite difference method right now. So we can model any shape. Yeah. So we developed 2 different methods. We begin with the adjoint gradient standard full waveform inversion. Because this method is straightforward. All equation is out there. We don't need to develop, we just implement it. Okay. And this method does not require a lot of memory to store the Jacobian matrix like Gauss-Newton method. So here we calculate the displacement residual, not the particle velocity. So integrate the data with time. So F here is solution of wave equations, and D here is the particle velocity from geophone. So when we use geophone, we measure the particle velocity. So we integrate it to get the displacement, calculate the misfit function, and then we calculate the gradient of the lamb's parameter, lambda and mu, by the forward and backward wave field. So forward is wave propagate from the source location, okay? And then backward is wave propagate from the receiver location, so convolve it. So standard full waveform method use Gauss-Adjoint approach.
So Kim, your backward solution meaning the solution from Adjoint equation, right?
For backward wave field,
Yeah.
we still use forward modeling, but just apply the source at the receiver locations.
Yeah. So it's Adjoint.
Yeah, that's adjoint. And then we determine the gradient for the VS and VP from the gradient of the lambda and mu. And then we also do the gradient conditioning. So here we use tempering to suppress the La gradient value near the source and receiver location. So we do a little bit trick here to remove the artifact. We did not solve it completely, just suppress it. And then also increase the contribution with depth. So we hope with this trick, we can do something. So tapering to linearly increase the gradient scale with depth to better resolve deeper structure. And then we do regularization to control the the roughness of the model. And then VS and VP at iteration n+1 is updated from previous iteration. And alpha P, alpha S here is optimal step length determined by parabola fitting. This method works very well for layer. Soil rock layer, it's identify it well. It's not so much for void. For void, we couldn't see it very clear because of the near surface artifact. We couldn't see it. So that's why we have to come up with Gauss-Newton again. Go back to Gauss-Newton for 3D. It took us several months to develop this thing. It's really difficult because we have to calculate the Jacobian matrix from the virtual source and reciprocal wave field. So to calculate the Jacobian matrix for all the cells harmoniously, not one by one. So we do the velocity residual again. We don't need to control with the reference trace anymore because now we have a drop weight. So basically we can generate very consistent source now. So for 3D, not very critical. And then
that depends on what it hits.
You mean hit rock and then you have a different signature?
On the surface, I mean, it depends on what it's hitting. But are you going along the pavement? Is that what you showed initially? Or is that in the field when you're moving along? Because the second one you showed you were in the field. Well, or I don't know if it's the second one, but the one where you identified the different voids, I think.
Yeah, that on the field, and then sinkhole also on the field.
Yeah, because I don't think your drop weight is going to be consistent on the field.
So, but at least a little bit more consistent than the hammer. That's what we think.
Yeah. Because you're hitting on a plate, or you're hitting on something bigger, so it doesn't penetrate.
Yeah.
Okay.
Okay. And then we also do the model updating and using the same equation here, and then this will help to filter the void. So M here is 20, 30,000 unknowns in 3D. And then J here, gradient or Jacobian matrix. This is a huge matrix. It's equal to number of cells, time number of shots, time number of receivers, and times number of time step if we do it in time domain. So it can easily go up to 10 billion elements easily if we store all of them in time domain. So we have to do in the frequency domain. So instead of storing 1,000 time step, we only store it for a few frequency. So we do inversion for 3 frequency at a time. So we calculate everything in time domain, but store in frequency domain and do inversion in time domain. So it's kind of hybrid time and frequency domain here. So we can reduce the required RAM a lot. Instead of 1,000 time step, we do only 3 frequency. So significantly decrease the required memory. So here we test it on synthetic 3D void first. So synthetic model with the layer on the top, rock at the bottom, the 3D void here. So the tested area is 24 by 36 meter on the surface and 18 meter depth. So 80 feet by 120 feet go to 60 feet depth. The void here 15 feet diameter embedded at 30 feet depth. So 2 diameter of the void at the center. We use 96 receiver, 8 by 12 put into 2D grid like this. So we have a triangle here receiver. And then for the sources location, we use 9 by 13, 117 shot at 3 meter spacing on the ground surface. So the tested area here is 24 by 36 meter on the ground surface. And we begin with a simple initial model again, increase with depth. We use the same initial model for both Adjoint and Gauss-Newton inversion. We did 2 inversions run at 15 and 25 Hertz central frequency.
So when you did that simple model, what's Poisson ratio?
1/3, it's just double.
Okay.
Typical value for soil. So we did it 1/3. So it took about 40 hours on a regular computer. So we need a supercomputer here. So we used a very good computer, 32 cores and 256 gigabyte RAM, which is a huge RAM here because we do the Gauss-Newton. So we need a lot of RAM. 40 hours. So each inversion run. So we stop at the same time for comparison, 40 hours. So each run took about 20 hours, about 1 day. Here's the result. Adjoint gradient method. And then Gauss-Newton at the bottom. So adjoint, we see the soil layer on the top, rock at the bottom, low velocity zone here. We do see something from the Gauss adjoint, but it's not very clear like Gauss-Newton. You see the Gauss-Newton right here, and velocity go very low. So it's clearer image because Gauss-Newton focus on the void. And we also have a 2D comparison here. So we get a plane at the center of the void. So this is 3D, but can you go back? So along this plane, okay, we plot it along this plane at the center of the void for detailed comparison.
Does it catch completely zero wave speed? I mean, I look at the scale, but you reconstruct the void, but it seems that its wave speed, I mean, your result, the void wave speed is not completely zero in your result.
Yeah, that is you can run the inversion longer. Right now we go about 180 meters per second right now. So the true model is 0. We cannot get it from the adjoint gradient. It just shows a low velocity zone here, about 300. So from the gradient approach, it's difficult to identify the void. We still see the anomalies there. Hopefully we put the invasive test down and then we can see it. Now, if we can recommend the anomalies location, it's still helpful, right? So large area, we tell them do only 3 CPT, it's still good, right? So we can still save some money. But we cannot distinguish the void or low velocity soil. Void or soft material is difficult to identify from adjoint gradient. But Gauss-Newton, you can see this one go less than 100 meters per second. Go very clearly. So that is 3D, and then we bring it to the field. So this is our first field application. So we did it in another dry retention pond in Gainesville. So different one. We see some chimney here. We hoped there are some void underneath, but there was no big void, so we couldn't find the void. But we identify low velocity zone there. So the test area is 36 by 9 meters only, so 120 by 30 feet. So we just our first attempt. We use 96 receiver in 4 lines. Each line is 24 receiver. So the blue circle here, receiver location. And we did 52 shots. That means the red cross here, using again the propel energy generator. So we had only 48 geophones. So we did it twice. So the stage 1, we put the 48 geophone in 2 lines, 24 geophone each line. We apply the load for all the 52 shots, entire grid, and then next. And then we move 48 geophone to the second half of the grid and repeat entire shot grid, 52 shot again, and then combine the data from 2 stages.
Right, but you didn't, I was confused. You said stage 1, why did you circled with your pointer down here below and we're stage 2, but you had nothing down there at that time, right?
Yeah, we just apply the source here and then wave propagate and measure here.
Okay. So you kept the receivers at stage 1.
Yeah.
And you put the source at stage 2. Okay, excuse me.
So stage 1, we put 48 geophone here and then apply the source for entire grid.
Right.
And then stage 2, we put 48 receiver here and then repeat it, entire grid. So each short location we hit twice. and measure by 48 geophone each stage and then combine. Because we have identical load at the same location, the same height, the same mass. So we apply the same load at each location. Maybe we increase the stiffness of soil.
So yeah,
more or less.
But, okay.
All right.
No problem.
Yeah.
Close enough.
How long does it take?
This one for data collection, it takes us about 4 hours. Propel energy generator is really quick. Just run and drop and run and drop every 3 meters, very fast. So we map all the location. It took 3 of us about 4 hours for the whole data set.
So the question is, did you use a rental vehicle for that to attach your system?
A good point.
Sorry.
Yeah. Because we may not see the vehicle again, right?
As an owner of vehicles, I know things can happen.
So here's the sample data from the 2 stages. So measure data combined, the wave very consistent in terms of magnitude and the pattern.
Yeah, that's a beautiful record.
Yeah, so 96 receivers and then time domain. Next. And we did analysis. So again, spectral analysis, have a shear wave on the top about 250, at the bottom about 400. We generate initial model like this. We did full waveform inversion using Gauss-Newton and karst Adjoint, 12, 22 Hertz central frequency, 2 inversion runs. It took about 30 hours each because the medium now smaller. Instead of 24, we do only 9 meter width.
So you have a couple modes there.
Yeah.
Maybe.
Yeah, you have something here. Yeah.
Something there.
Something here.
Down at
Low
the
velocity zone, something.
Okay.
All right, I have a 0 minute, so I'm going to wrap it up.
Same thing to me. Don't worry, Kim.
So, both method can match data very well. So you can see here estimated data is the red waveform, and then observed here is the blue line. It's a little bit mismatched here, but match very well, both methods. So there is some hope if we can match the data. In many cases, we cannot match it.
I'm not sure in the bottom left you plotted both lines, to be honest.
This one?
Well, I don't see the second line very well. I'm just teasing you.
Yeah, I know.
We're on top of each other many times. Yeah.
All right, let's some hope here. All right, this is the result, 3D result. Soft material on the top, limestone at the bottom. We have a shallow limestone here. And then some low velocity zone here near the chimney, kind of. Adjoint method, Gauss-Newton method, both work well in this case. I would say the results are very similar. Next. Here's the comparison in 2D for different planes. 3D result, but I show it in different plane. So you can see it, low velocity zone here from karst Adjoint, Gauss-Newton, also similar, I would say. Shallow rock here and deeper here. So we have a low velocity zone around the chimneys, but there's no void.
When you say the Y3, is that
So,
those 4 lines?
Yeah.
So those are the 4 lines.
Yeah.
1, 2, 3, 4, basically.
yeah.
Okay.
So Y equals 0 and 120 feet long, Y equals 3 and then 6 and 9 meters. We also did 4 different SPT near the chimney at the distance 24 meters.
Yeah.
And here's the result.
So that looks like it's pretty consistent. I mean, in general, over the whole
Area.
4 lines.
Yeah. Very consistent. Change it. So you have shallow rock here and deeper rock here. And here's the SPT. Next one. Here's the comparison.
Did you have a feel for that? It looks like the lines were well set up or well located. Looking at the surface, did you have a feel for where the void might be?
We do next to a chimney. So we just 24 meters further.
Where it wasn't the surface.
Yeah.
It was the hole there.
Yeah, but it is nice to see that, to try to do what you just did. Yeah.
So here, the blue line here is karst Adjoint, and then the red line here is a Gauss-Newton. So we have a low velocity zone here, here, mismatch here between 2 methods. But generally, they show the trend. So low velocity zone about 4 or 5 meter, and then increase with depth, limestone about 10 meter depth here. So we got something. It is our first attempt for 3D field application. So hopefully we would get better result with the data man collected yesterday. So with really beautiful source and.
Okay, that's, so we want your input on what you would like the source to do.
We did it already.
Perfect. I mean, because that's, yeah, because I know you were here doing those tests, and that's important to us to see how that works for you.
So I have a few conclusions here. Both shear wave and P wave can be characterized at high resolution, meter pixel down to 20, 30 meter depth, maybe 20 is safe. By 2D and 3D methods, Berry void can identify to a depth of about 3 diameter of the void from 2D analysis. We don't know how deep we can do with 3D. So 3 diameter of the void, deeper than that, we don't see it very clear. We still see some soft material there. It's not really clear void. Gauss-Newton tend to provide better result compared with Gauss-Adjoint method. Future work, we will do viscoelastic waveform.
I ask one question, and they may be talking about this. So you always are using vertical, and you had thumper vertical. What if you put it horizontal?
We don't know.
Okay. Because you got P mainly going one direction and shear going in the other direction, let's say. I don't know. But would that
It would be better, I think. I think lateral would image the layer interface better. We share in this direction.
That
So,
sounds like an NSF proposal to me. Okay, good.
So we are working on 3D viscoelastic waveform now. I have one student to work on that. So we want to account for material damping into the forward modeling. So hopefully we can extract more material property like seismic attenuation, like QP, QS. We also do the adaptive mesh waveform now. So we want to begin with uniform grid to identify the anomalies, and then we will use refinement mesh at the anomalies to see things in more detail. And lastly, the acknowledgement. So this research is funded by FDOT, Ohio DOT, National Science Foundation, and Federal Highway Administration. And that is teamwork result. Our research team, including Dr. Markway, Dr. Hiltonen, Dr. Washman from UF, Dr. Hohota from FDOT, and myself, Kim Tran from Clarkson, and several of my students at Clarkson University, Trung, Brian, Duminidu, Justin, Marjit, and Amela. So thank you all for the contribution. We have a few publications here. The top one still reviewed by Geophysics for 3D, the rest are available. What else? Last one is just thank you, and hopefully I can answer your questions.